Equilibrium constant, lecture 19. So we're going to move away from talking about kinetics and start talking about these reversible reactions. We introduced these in 111 in the first semester, talking about reactions that can go in either direction in terms of solubility. So weak electrolytes can dissolve and then reform their compound. We're going to talk for this chapter and the next couple chapters, focusing on these equilibrium reactions, so reactions that can go in both directions. So let's look at one of these reactions. We have N2O4 can break apart into two NO2 molecules, but those two NO2 molecules can reform this N2O4 molecule. Right? So if we start with only the N2O4, like in this figure here, right? If we follow those concentrations with time, we see that the N2O4 concentration goes down as some of the NO2 is formed. Right? And then after a certain time, the concentration stops changing. Right? And we can see the reversible reaction is true if we start with only NO2, like in the middle here. We can see that as that concentration is going to go down as some of the N2O4 is formed. And in fact, the N2O4 compound actually ends up with a higher concentration than the NO2, even though we started with primarily NO2. But again, at some time, the concentration appears to stop changing. Right? We end up with a stable concentration of both species. Right? And in fact, in this last one, over here, if we see that if we start with some concentration of both of them, they're going to then react until, for some time, the concentrations are going to change until we get to this stable arrangement where it appears that the concentrations are stable. Right? And this is what we mean by equilibrium, that we get to a certain point where the reactions appear not to change. Right? So an equilibrium is a state in which there is no observable change with time. And kinetically, the reaction doesn't stop. It's still going on, but the forward reaction, the reaction that reactants are going to products, so that speed, is equal to the speed for which then reactants are going, or products are then reforming reactants. So the reaction is still going on. It's a dynamic equilibrium. We still have reaction going in both directions, but the speeds are the same. So it appears that the concentrations are not changing. So the chemical equilibrium is achieved when these rates of the forward and reverse reaction are equal. And the concentration of the reactants and products remain the same. The individual molecules may be changing, but the overall concentration is going to be remaining constant. And we've sort of also talked about this in a different way in the sort of physical equilibrium, where we can talk at the boiling point, there's an equilibrium between water as a liquid and water as a gas. That's what we refer to as a physical equilibrium. What we're going to talk about now mostly are these chemical equilibrium, where the reactions are occurring until the reaction rates become constant. And we can describe, we go back to this original example with the N2O4 and the NO2, in all of these cases, we see that the reaction occurred until the concentrations remained constant. The concentrations, though, were not always the same. Right? It depended on where we started. But there's got to be some relationship, because in all three examples, the N2O4 ended up at a higher concentration than the NO2. Right? So there's got to be some relationship between those. And in fact, if we look at the initial concentrations here, the concentration at equilibrium, we see that at equilibrium the concentrations are always different. But there's got to be some relationship to it. If we look at a 1-to-1 ratio, where we look at the NO2, the amount of products divided by the amount of reactants, we see that we get not a constant number. But if we square that NO2 concentration and divide it by the N2O4, in all of these reactions, we still get the same value, or approximately the same value. Right? So it appears that these reactions are going to this sort of relationship of mass, which we're going to refer to as this equilibrium expression. Right? So if we look at our reaction here, we see that we get a constant value when NO2 squared divided by the concentration of N2O4. Right? We always get this constant value of 4.63 times 10 to the negative 3. Right? So we would say the equilibrium expression for this is just the concentration of NO2 squared divided by the concentration of N2O4. And if we look at the balanced chemical equation, we're always taking the products raised to their coefficients divided by the reactants raised to their coefficients. So if we drop down here to this general equation, AA plus BB is in equilibrium with CC and DD, then the equilibrium expression for this, based on the law of mass action, is going to be the concentration of C raised to its coefficient, lowercase c, times the concentration of D raised to its coefficient, lowercase d, all divided by the concentration of A raised to its coefficient, lowercase a, times the concentration of B times its coefficient, lowercase b. And this K value is really going to tell us a relationship of where equilibrium lies in relationship to the products or reactants. If we see here that K is much greater than 1, right, that says that if we look at our K expression, the top number, to be greater than 1, the top number has to be bigger than the bottom number, which means that we have more products than reactants overall. So this is what, when K is larger than 1, much larger than 1, we say this is a product favored reaction. We're going to have more products at equilibrium than reactants. Conversely, if we look here where K is much less than 1, now the top has got to be smaller than the bottom, which means that equilibrium is going to lie to the left, or where we have more concentration of reactants, or this is a reactant favored process. Right? So the value of K is really going to tell us how likely where equilibrium lies. Is it we're forming more reactants or more products? Which are we going to have more of at equilibrium? So the focus of this lecture is really to get you to understand these K values and how to write them. So let's go over some rules for writing these equilibrium constants. So the equilibrium concentration of the reacting species in the condensed form, so we're always taking the concentration of products divided by the concentration of reactants raised to their powers. The concentrations are typically expressed in molarities. For something in the gas phase, we can either talk about it being in a concentration in molarity or a pressure, because we can talk about partial pressures, remember from the gas chapter, in atmospheres. The concentrations of pure solids and pure liquids, those solvents or the solids, do not appear in our equilibrium constant expression. Remember when we talked about this theory of reactions, the collision theory, that those two reactants had to be in the same phase and collide with the appropriate energy. Right? If they're not in the same phase, then they're not going to react. Therefore, we're going to ignore them in this equilibrium expression. We're not really ignoring them. We're setting them equal to 1, raising to a power of 1. So they're sort of stable. Their concentrations remain stable. They're not involved. By convention, all these equilibrium constants are dimensionless. Right? So we're not going to worry about the units on these equilibrium constants. They're all dimensionless. All of these reactions have to occur at a specific temperature. So if we change the temperature, we will change the equilibrium position. So when we talk about an equilibrium, we're talking about the equilibrium for a specific reaction at a specific temperature. If you change the reaction or reactants or change the temperature, our equilibrium expression value is going to change. And if the reaction can be expressed as the sum of 2 or more reactions, we've done this several times, then the equilibrium constant of the overall reaction is given by the product of the equilibrium constants of the individual reactions. So if we we add two reactions together, we're going to multiply their equilibrium constants. If we subtract, we're going to divide. So it's the same process that we had before. So we're always taking these equilibrium constants and multiplying them together. We can talk briefly about the two different kinds of equilibrium. We can have what we call homogeneous equilibrium, where everything is the same phase. So all gases are all aqueous, for example. So if we look at this first reaction that we've been doing, this N2O4 as a gas to 2NO2 as a gas, we will see that that is an homogeneous equilibrium. They're both in the same phase. The reactants and the products are in the gas phase. So we can then express this one as either what we call Kc, the equilibrium constant in terms of concentration, which is the concentration of the reactants, in this case NO2 squared, divided by the concentration of the products, N2O4, or the equilibrium constant in terms of the pressure. The partial pressure of NO2 squared divided by the partial pressure of N2O4. Right? So if we're homogeneous, we can talk about these, and it's a gas phase, we can talk about these two different types of equilibrium. Kc, the equilibrium constant in terms of concentration, or the equilibrium constant in terms of pressure, Kp. Right? Right? If we look at this, another example, we see in this case the water is a pure liquid, so it's going to be constant. We're not going to include it in Kc at all. Remember, we said we don't include units. Right? For these homogeneous reactions, we can then convert between Kc and Kp. They're not all, in most cases, they're not going to be numerically equivalent. Right? They're not going to be the same number. But we can convert them by using our ideal gas equation, so that the equilibrium constant in terms of pressure is equal to our equilibrium constant in terms of concentration times RT raised to the delta N, where this is the change in moles of gas in this reactant. So the delta N is the moles of gas in the product minus the moles of gas in the reactant. And so from our balanced equation here, if these are all gases, then it's going to be C plus D minus A plus B. Right? We can also talk about heterogeneous equilibrium, where they're in different phases. Right? We can talk about gas here. Typically when we get this, we're going to typically always put them in terms of Kc. In this one, even though we have different phases, the only one that's involved in our equilibrium constant is the CO2, so we can express it as Kc or Kp. Remember, the solids and the liquids are not in our equilibrium expression. They are considered constants, so we ignore them. So this equilibrium expression, this capital K, gives us an idea of where equilibrium lies. Right? We can always look at where we are in a reaction. If we know the concentrations we have currently, we can get an idea of where we are in relationship to equilibrium by solving what we call the reaction quotient, which is Q. It's calculated by taking the concentrations that we know and substituting them into the equilibrium expression. So it has the same form as the equilibrium expression. We're just not sure we're at equilibrium. Right? So if we do this calculation with QC, or Q, we have one of three things that can occur. Either Q can be greater than Kc, which means that we have more products than we should at equilibrium, so the reaction is going to move from the right to the left. So if Q is greater than K, we're going to move some of that mass of the products back to the mass of the reactants as we approach equilibrium. If Q is equal to K, then we are at equilibrium. There's going to be no shift. If Q is less than K, that means we have more reactants than we should at equilibrium. So we're going to shift some of that mass from the reactants to the product. So we're going to move from the left to the right as we approach equilibrium. So you can see that in this bottom equation. Right? So we're going to be setting up these Q's, comparing Q to K's in the lecture, and converting between the two forms of K.